Hello, folks. How are you? The microphone works, right? Yes. So, my name is Graziano, and I'm from Italy, and that's why first, my name seems so weird. Second is why my face seems so tired, because we are 7 hours ahead in Italy, so now it's basically my time to go to the bed. And third is why my accent doesn't look like a native speaker, native English, because my primary language is Italian. So, I'm a developer relation buddy in Mia Platform, which is an Italian product company that bring on the market internal developer platform builder, which is a product that helps organization to build exactly the kind of platform we are going to talk about today. I started to proposing contents to conferences and writing articles about my main focus area, which is platform engineering and developer experience. And in the last few months, I started to propose different kinds of contents, trying to blend the platform engineering and developer experience area with other topics. I did it with observability, and now I'm here to talk about platform engineering, internal developer platform, powered by different artifacts, different runtimes. So we are trying to propose the perspective of how an internal developer platform looks like without the combo of Kubernetes and containers, which is actually the standard in the industry right now, and replacing it with WASM components. Let's start with a few groundworks. So let's start to understand what is an internal developer platform and what we are talking about when we talk about platform engineering. Some of you already built or use an internal developer platform inside their organization. Raise your hand. Oh, just one. OK. So, when we talk about platform engineering, we are talking about methodology. And the main goal, the final goal of this methodology is engineering enablement, OK? How we can get this engineering enablement, how we can let the developers, the engineers in general, do their work at the best way possible. We do it by build or adopt an internal developer platform, which is the tool at the heart of this methodology. There is not a standard path, and there is not a one-size-fits-all solution to build platform, because it aims to solve problems. And if each company have its own problem, it's natural that every platform differs from each other. But if we have to give a standard definition of the platform, we can say that it's a common place, where you can create and share value inside the organization. And basically, it's composed by two things. The first one is the capabilities, provided mainly by the platform engineers. And the second one is the interaction. So the ways that the engineers, those who consume the internal developer platform, can access these capabilities. At the heart of the IDP, the internal developer platform, there is a sort of value cycles, where we want to basically achieve a circularity of our software assets. We have some who build something, it doesn't matter what. What matters is that the value of the software artifact is recognized, standardized, and made available to the others. Others, which are the consumers, that takes value by using what the creators did previously. And all this process is orchestrated and managed by the platform engineering, the platform engineers, sorry, which basically do all the abstraction and the standardization work to make these assets available to everyone. And we can say that in this vision, the platform engineers are basically the curators, OK? Let's try to understand how we can figure out a platform. From the left to the right, we have the capabilities. Mainly, we can clusterize these capabilities in three main groups. The first one is self-service capabilities. Most of companies, in my experience, start approaching the platform to automate and make the developers autonomous in terms of accessing infrastructure, okay? We all know the so-called ticket traps. You need to start a new project, so you open a ticket, you have to open a ticket to the ops and waiting for days to have the access to a group on your Git providers, the access to a cluster or namespaces, and we want to avoid them. We want to make the developers autonomous in terms of getting the infrastructure they need. The second one is the one that enables us to create this circularity. It's the software catalog. It's basically a marketplace of components where everyone can take something from the bucket and add something to contribute to it. And the last one is the one that helped to solve the complexity of the DevOps tooling automation by standardizing the interaction and made it available maybe through simple APIs or nice web interfaces. The other two components are the internal developer portal, which is basically the main interface the developers can use to access the capabilities, and the platform orchestrator, which is the glue between the capabilities and the internal developer portal. We will see later how it works. So let's try to understand how a simple project creation works. To let the developers autonomous to access and start their work without adding dependencies between teams, basically our platform engineering team needs to handle three different tools. A runtime, and usually in the traditional model, we want our workloads to run on Kubernetes. A pipeline runner that help us to deploy all our workloads on the cluster, and the configuration repo, which is basically a Git repository where you store all the configuration for your services, the manifest, for example. The work of the platform engineers is to anticipate this need. Instead of waiting for a ticket, they configure all this stuff once and made it available through the platform orchestrator. So what happens when me, as a developer, have to start a new project? I open the internal developer portal, add the metadata that describe the project, like the name of the project, which environments I need, test and production, for example, where my Git repository should be stored, and something like that. And the first thing that happens is that a namespace, maybe a namespace for each environment I need, is created on the Kubernetes cluster that is already provided by the platform engineers. It's all automatic. Then, doing so, we just need the runtime layer. We need also something that helps us to deploy and abstract all the interaction with the delivery tools without actually doing something on Kubernetes. So we need a configuration repo where the project configuration is stored, and a pipeline runner, which is triggered each time we want to deploy something on one of these environments. On the bottom right of the image, you see a software catalog. Software catalog is the capability where you can access to get some templates to start doing your work. Let's do a zoom in. You can find already ready components like, I don't know, I need a API gateway. I get it, add it to my project, and start using it without care more about how it works. I need to start my CRUD application. I have a lot of different templates, like for Spring Boot, just to take one example. What I need? Clone the templates where I have all the boilerplate code, the Docker image, and the pipeline that build the artifact in the end. Clone it, write my logic, push it to the service repo, and when I push the the code, the pipeline runs, build my artifact, and push it on a container registry, like, for example, Docker app. What happens then? The platform orchestrator do its magic. Which is the magic? Is that translate the intent of the developer by using the internal developer portal to Kubernetes manifest. So developers don't have to write by hand the Kubernetes manifest. And when you need to deploy, just click few buttons on a fancy web UI, and the pipeline is triggered, and based on where you want to apply this configuration, the code is released. But this is actually amazing because you standardized a lot of complex tooling, but that's really powerful, but probably overkill for simple use cases, like, I don't know, validating symbol policies, creating batch processing, integrating, working with files, or even create some function that have to run just one time per day. For this kind of use cases, there is not an alternative to a full-blown containers and Kubernetes platform. The answer is yes, because instead I will, in Italy and not here. The answer is yes, and the alternative is WASM, or WebAssembly. Some of you already know something about WASM or WebAssembly. Raise the hand. Again, just one. So, WebAssembly is not a new programming language, first. Second, is not just for the browser, as the name suggests, but is basically a compilation target. It's a low-level and portable binary format where, well, you can basically compile your code written in any programming language, basically Python or Go, Rust, and many others, to these portable binaries, okay? And which is the difference with containers? When you do a container, you basically wrap an entire system just to run your application. That means slow startup times, because you have to wait the container to boot. This means larger weight in terms of size of the container. And this also means faster, lower startup time, okay? With WebAssembly, you just shipping your code. No, you don't have to package it with our operating system or any other system libraries. Trying to do a comparison with WebAssembly and the container artifacts we can have. Difference in startup time. Containers, even the tiniest, takes from few milliseconds to few hundreds of milliseconds to few seconds to start. Just because we have to wait the containers to boot, and that's even more if we want to schedule it on Kubernetes. WASM components takes just few milliseconds. It's a binary, you don't need to boot nothing. When you need it, it's already available. Size. A containers is heavy. Even the easiest microservice weighs weighs hundreds of megabytes, okay? The WASM components is basically few megabytes. We are talking about 1 or 2 megabytes. The isolation of the workload. WASM comes out of the box with a native sandbox, okay? Is everything you build with the WASM is natively sandboxed from the environment where you run it. Containers use Linux features like namespaces and C groups, which are great, but I have probably attack surface. Another one is the portability. Containers need to be built on a specific architecture and a specific OS level. And trust me, I know well how it feels when you are at 2 a.m. doing something on your local machine, which is in my case ARM macOS, and you want to deploy it on a Linux server, for example. That's not work. You need to rebuild it, and at 2 a.m. is not the best thing to do. Again, we saw how change the artifact. We need also a layer that orchestrates all our components. This layer is wasmCloud. It's like having Kubernetes, but for WebAssembly. There are basically 3 different components. And to describe it, look at the image. We have the wasmCloud host, which is basically a lightweight process that runs our components, our WebAssembly components. We can have 1 host or even hundreds, and all together forms a sort of network. This network is called lattice. Lattice is a distributed mesh of all your hosts, and basically its function is like a discoverability for the host, a layer for communicating between the hosts and stuff like that. The application, the host can run everywhere, from edge devices to VMs to even Kubernetes, like this example. The application is composed by 2 components. The components, or actor, which is where you run the logic, is a stateless WASM module, and the capability provider. The capability provider is another module, a plug-and-play module, that exposes something like HTTP servers, database access, or key-value storage, for example. How the anatomy of the platform change? This is not a disruptive change, but we have some little changes that are worth explaining. Platform engineers are not anymore delivering Kubernetes cluster, but they manage the lattice, the wasmCloud lattice, giving the developer access to hosts, okay? Oh, sorry. Then we need also an application manifest repo, because we need to describe how our workload behaves. And wasmCloud adhere to a standard, which is an open application model, okay? And you basically can describe in a manifest like you did for your Kubernetes manifest. And then we need something that handles the deployment of the workloads to the host, which is in this case Argo CD. Let's zoom in again and see how the component catalog changed. You don't have any more templates for full-blown microservice with SDKs, libraries, or something like that. You just have tiniest templates for building the components or the provider. The developers doesn't change anymore in the process, and doesn't change nothing in the process. They clone the templates, write their logic, push the code on the function repository. The pipeline doesn't build a container artifact, but a WASM binary, and this binary is pushed on OCI registry, Open Container Initiative, right? But not packaging it as a container, but as a WASM binary compliant to the OCI. Then, the platform orchestrator do its magic again. Convert the intent of the developer into the OAM manifest, and when the GitOps tool detects the changes, it deploys it on the lattice. We are near the end. Let me wrap up the benefits of this methodology. First, simplicity and strong decoupling. One of the promises of microservices is decoupling the business logic to anything else, okay? But with wasmCloud, it enables a strong decoupling of these concerns, because components and providers communicate together through contract interfaces, okay? So you basically write your logic as component, and then you can bind it with some provider, which could be written by you or made available by platform engineers. This is probably the most important slide for my talk, is how we change the concept of application composability. With a traditional model, is a static composition at design time. You use the software catalog, reuse and adapt the component you find on the software catalog, and deploy something new. It's all at the design phase. With wasmCloud, you can use the standard model where you write and package your components and provider together as a single unit and deploy it, or you can just deploy your component and bind it to something that is already running on the host. We are talking about the last benefit, which is the resource management, the saving in terms of resources. When we are using containers, even when they are idles, they are not exactly free. They use RAMs, and they use always some CPUs, thanks to background processes, for example. WASM components, since they are basically stateless, when are deployed and not in use, they didn't use nothing. And that's a benefit from 3 different areas. Cost, you are not using nothing from your cloud provider. Environmental cost, because if you are using resources, you have a CO2 footprint. And then also because the performance is better. The startup time, as I said, is less than the containers. And the runtime overhead, you just have your host, which is a lightweight process and not the full-blown Kubernetes and container runtime. That's basically the end of the presentation. If you want to get in touch with me, you can scan the QR code that is my LinkedIn profiles, where you can chat, talk about platform engineering on the DevOps, and ask also questions if you want.